expanded, raising the temperature of 45 liters of water by 75 centigrade, assuming the efficiency of the heating equipment to be 90%. So we are asked to find the electrical energy or the electrical consumption of this heating equipment, which is used to heat 45 liters of water to raise the temperature by 75 Celsius. And that heating equipment has an efficiency of 90%. As we all know, efficiency has a general formula of output over input. So in this case, the electrical energy is the consumption or the energy consumed by this heating equipment. So that is actually our input. So we are asked here to find the input. So manipulating this particular formula, it will be input is equal to output divided by efficiency, where efficiency is given, that's 0.90. How about the output? So what is the output of this heating equipment? Of course, the output is the heat or the thermal energy transferred to the water. And since this water is heated, it has a temperature rise. And if there's a temperature rise, meaning the heat is sensible. So for sensible heat, we have a formula of MCP delta T. So that is our output. So our input or the electrical energy is our sensible energy, MCP delta T, divided by efficiency. Okay, so for our electrical energy, it's equivalent to M, that's the mass of our water, Cp is the specific heat, and delta T is our temperature rise. So do we have a mass? So reading again the problem, as you can see, no mass is given. What we do have here is the volume of water, but we can still find the mass by using the density of water. So from the density formula, rho is equal to m over v. So the mass equivalent to density times volume. So we must also know the density of water, which is 1 kilogram per liter. And our volume is 45 liters. Cancel. So that is actually mass. So as you can see, our mass is also 45 kilogram. For the CF of water, that's 4.187 kilojoules per kilogram Kelvin. You can cancel out kilograms. And for our change of temperature, that is 75 centigrade. And take note, the change in Celsius is also the change in Kelvin. Then divided by our efficiency, which is 0.90. So we have here electrical energy in terms of kilojoules. But as we can see, our choices are expressed in kilowatts. So we must still convert our answer. So how can we convert kilojoules into kilowatt per hour? So it's easy. Just multiply kilojoules by the number of hours per second. We know that 1 hour is 3,600 seconds. So we can see that kilojoules per second is kilowatts. That would be kilowatt hour. What is our electrical energy? So what is our required kilowatt hour of energy? That is equivalent to 4.36 kilowatt hour. Instrument that measures density, that is hydrometer. To what height will a barometer column rise if the atmospheric conditions are 13.9 pounds per square inches absolute and 68 degrees Fahrenheit, and the barometer fluid is mercury? So as we all know, there's a given height for a barometer column, so pressure is gamma times H. And since our fluid in the column is mercury, so this would be a specific weight of mercury times height. So our height will be actually pressure divided by gamma of mercury. So what will be our solution here? So our H will be equivalent to, the pressure is 13.9, that's pounds per square inches. So let's convert that into pounds per square foot, and we can see later why. So we know that 144 square inches is equivalent to 1 square foot. Cancel. Divide by our specific weight of mercury is just equal to the specific gravity of mercury times a specific weight of water. So it is common knowledge that the gamma of mercury is the Sg of mercury, which is 13.6, times gamma of water, which is 62.4, which has a unit of pound force per cubic feet. We can cancel out pound force, and we can cancel out square foot. So the remaining unit of our height will be in foot. But the choices are in inches. So let's convert that. So it is common knowledge also that there are 12 inches in 1 foot. So what is our height in the barometer? This is equivalent to 28.30 inches. For number 14, this law states that the pressure applied to a point in a confined liquid is transmitted equally to all other points. So that is Pascal's law. Number 15, to what height will a barometer column rise if the atmospheric conditions are 13.9 psia and 68 degrees Fahrenheit and the barometer fluid is ethyl alcohol? Note, at 68 degrees Fahrenheit, our vapor pressure is 122.4 pound force per square feet, and the specific gravity is 0.79 for ethyl alcohol. So just like our previous calculation, we have pressure, it is the specific weight of the fluid, which is ethyl alcohol, times the height of our fluid. So again, our height is pressure over specific weight. Okay, so this will be pressure in the numerator. So our pressure is 13.9. So that's PSIA again. So just multiply it directly by 144 to make it pound force per square feet. So that is our pressure in the numerator. If no PV provided, but in this case, our vapor pressure is given. So our pressure actual in the atmosphere, which is measured by the barometer, is actually the atmospheric pressure 13.9 minus the given vapor pressure. So that's 122.4 pound force per square feet. So if it happens that no PV given, so you can neglect that. But if it is given, you must include this in your calculation. So that will be our pressure actual, and divide by our gamma of our ethyl alcohol. So we don't have our gamma directly, but we could get that by multiplying the specific gravity, which is 0.79 times the gamma of water, 62.4. That's pound force per cubic feet. We can cancel out all our pound force, and we can cancel out square foot. So our answer is in feet, but the choices are in inches. So you can convert that to 12 inches. So what's our height? It is equivalent to 457.45 inches. The temperature at which its vapor pressure is equal to the pressure exerted on the liquid. So this is the boiling point. Number 17. So we are asked here for the capillary rise in our capillary tube. So for our height in the capillary tube, so that's equivalent to the 4 times our surface tension times the cosine of the contact angle divided by the specific weight times the diameter of our small capillary tube. So let's substitute our given. That will be 4 times our surface tension is 0.00156 pound force per feet, multiplied by cosine of our contact angle, which is 0 degrees, divided by our gamma, or the specific weight of this fluid, which is ethyl alcohol. So we need the specific weight, but we only have the density. So we know that the density and the specific weight are actually different, but they are related. But take note, for problems like this which has English units, take note that the density and the specific weight, they are numerically equal. How? So if our density is 49 pound mass per cubic feet, and we know that the specific weight is expressed in pound force per cubic feet, the density and specific weight are actually numerically equal. So meaning, if this is 49 pound mass per cubic feet density, our specific weight is actually 49 also, but in pound force per cubic feet. So that is proven. So density and specific weight are numerically equal, but they only differ in our units. That's our gamma, and the diameter is 0.005 inches. So we can see our dimensions are expressed all in feet. So we must convert this 12 inches in 1 foot. Okay, we can cancel out pound force. And we can cancel out 2 of the feet. So the remaining unit of our height is in foot. What is our capillary rise? So this is 0.3056. Type of turbine that has high pressure and low pressure is called compound turbine. 19. Compute the specific volume of an air vapor mixture in cubic meters per kilogram of dry air when the following conditions prevail. The temperature is 30 degrees Celsius. Our specific humidity is 0.015 kilograms of water vapor per kilograms of dry air, and the total pressure is 90 kilopascal. So we are asked to find the specific volume. So for an air vapor mixture, our specific volume is RT over P, where R is our gas constant of air, T is the absolute temperature of our air, and P is the air pressure, which is the difference of the total pressure and our PV. Okay, so R is constant, temperature also given, and PT also given. What we don't have is PV, but we do have the specific humidity, which has a formula of 0.622 PV over PT minus PV. Given. So we can solve our PV. Okay, so let's calculate first our PV. So our specific humidity is 0.015. That's 0.622 times PV over PT, which is 90, minus PV. What is our vapor pressure? So that is 2.12 kilo pascal. So we can now solve our specific volume. So our R is 0.287 kilojoules or kilonewton meter per kilogram Kelvin. That's our temperature, which is 30 degrees Celsius. To make this Kelvin, we must add 273. Divided by PT, which is 90, minus PV, 2.5. So that's kilopascal or kilonewton per square meter. Kilonewtons cancelled as well as Kelvin. So square meter in the denominator times meter in the numerator, that will be cubic meter per kilogram, a unit of a specific volume. What is our answer? So the answer is 0.99 cubic meter per kilogram. The design of an air supply duct of an air conditioning system affects the distribution of air.